In this video, we'll be continuing the work on the coil winder. As you can see, I've got the frame parts cut, I've got all of the holes drilled, and I have the base cut, sanded, and finished with some oil finish. Today we're going to be turning and soldering some brass bushings that will go in those larger holes and act as guides for the spinning rods that make this thing function. The coil I'll be using is a 1/2 inch diameter, and I'll be using this 1/2 inch brass bar, which I showed you in the first video, to make some bushings. I have this obscenely big marker here. Obscenely big marker is going to be used to make markings on the brass. And what we will actually do is turn the lathe down to a low RPM. Put some blue marking on the brass rod. The blue marking will allow us to scratch measurements into the brass rod, and it gives us a visual reminder of where we want to cut the brass. Another thing I'm going to use on this operation is this dial indicator with a magnetic base. The magnetic base allows it to stick pretty much wherever I want it, and by tightening this knob I can get this arm to be more or less compliant and move it around as I need. You might have noticed that my lathe kind of growls when it runs. The reason for that is because I have 18 threads per inch dialed in on the gearbox. If I change out for the regular power feed gears, I would be able to get a more smooth operation that wouldn't sound so objectionable. Almost forgot. When you dial in your depth of cut, you want to lock your cross slide. That way it doesn't move on you when you're trying to turn down to a shoulder. My lathe doesn't have anything fancy for doing this. I just have to turn one of these screws, presses up against the gib. For this operation, I'm going to show what the dial indicator does when I make the cut.
The dial indicator tracks the position of the carriage so I know where the tip of the tool is. I'm not going all the way so I can clean up later.
So that's a depth of 180 thousandths. You notice that when I turned it back more than I turned it forward. So I'm currently sitting at 100 thousandths away from the end of the work, and that allows me to get the micrometer in there. I've just made the final turn. I'm going to make a measurement. It's important that when you make measurements, you use a file or other tool to take the corners off of the edge, because those corners often have burrs on them from turning, and if you don't deburr them, then you get a false measurement. Okay, we are sitting right at 370 thousandths. Camera will focus, it will show that very clearly. 370 thousandths, right where I want it to be.
Now that I've turned one surface of the bushing, I'm turning down to the flat surface created by the shoulder. This is so that all of the rings created by repetitive turning operations are all smoothed out and I have the correct dimension.
Another thing I did is after I scooted out and shaved off the inner surface of that step, I went back in and put a little divot in the top of the corner of the step here, and what that will do is prevent any sort of internal radius from interfering with sitting down in that hole. Like I said before, we want this to sit flush in the hole. If you're making parts that screw together, you want to make sure that happens so you don't run into problems with fitment. Sometimes the screwed in part won't fit in all the way. going to walk our tailstock, feed it in just a little bit. The center drill finds its own center and you press it in nice and easy. I didn't even have to up the RPM. I've got the 3 drills I'll be using and the reamer laid out on top of the lathe compound. I'll start with a 1/8 of inch bit, go up to a 3/16, and finish off with a 15/64 here. Stepping up that way takes the stress off each individual drill bit and makes it so they only have to remove as much metal as they need to widen the hole. This is a reamer. This is a 1/4 inch reamer. It's a accurately ground tool used to make a hole that is very near 1/4 of an inch into a perfect 1/4 of an inch, and also make it perfectly round. Some rules for running reamers are you never run them backwards because you'll damage the blades on them. There are, looks like 6 blades on here. You run them slow with oil, unless you're doing cast iron, I guess. I've been turning this brass dry and it hasn't been a problem so far, but you just want to keep them very nice and clean and be gentle with them because they're an accuracy tool, not a metal removal tool. The drill bit will be cutting the outside edges of the hole only, so when it hits the bottom and starts cutting fresh from the center, I'll be able to feel a difference in the pressure, and that will be able to be a gauge in how far I need to cut. Is it perfect? No, because it's going to lengthen the hole a little bit, but a little bit being the key. When I think I've got it, now it's time to take a measurement and drill all the brass pieces off. (15/64), ladies and gentlemen. Another way to tell the depth of the hole, if I don't have the ability to put markers on my tools, is if I were to go over here to the tailstock, you see these marks on the quill, and I can use those to count down the millimeters or the 1/8 of an inch depth. I also have a fine feed marking on my tailstock. If I really wanted to get precise, I could use those, although I think that the best way to do that would be with a micrometer. So I'm going to go at this again. Use the WD-40. I'm going to put some on the reamer. I'm going to slow my lathe down a little bit. My lathe has been screaming at something like 900 RPM. Stock off. Shut off the lathe. Alrighty. Again, analog micrometer says feel out the bottom of the hole and see where the exact parts of the hole lie, so that I have about 3/16 of an inch between the back of the scribe mark. No, it's more like a 1/4 of an inch between the back of the scribe mark and the end of the wire. So I'm going to have about a 1/4 inch of hole where I didn't necessarily want a hole. However, if I don't move the brass, I may be able to get another bushing cut out of this. So, next step I'm going to do is put a countersink bit in the hole like I did for the steel parts. Countersink bit in the tailstock chuck, and I'm going to chamfer over those inside edges of that hole, so when I try to put a rod through there, it's not going to catch, scratch up the rod, or wedge it in the hole, or none of the above. This operation isn't about putting marks in their place. It's about taking the existing edge and putting a gentle slope on them. That'll also kind of allow us to put some oil in there too, because if it has a little kind of cup shape at the end, you can tilt the bar up, put a drop of oil in there, and then rotate the spinning rod around inside. Run the parting blade slow, maybe 100 RPM. We're at 96 RPM, which is good. I'm going to use my carriage lock to keep my carriage from moving. Begin cutting. Some people, including myself, like to take a minute here, get a small file, get in here and chamfer this inside edge while it's still attached to the lathe. It's a lot trickier to do when the part is too small to be held. Pushing your blade slowly but firmly into the work. Your chips should look like little ribbons that are curled as they come off, not tiny little dusty flakes. Keep going, keep going, keep going, keep going. Okay, and we have our part. I have 6 bushings. Some of them have rough edges on the front and back. I think I'm going to put them on a flat piece of tile with some sandpaper and smooth those out. 1, 2, 3, 17, 18, 19, 20. Okay. So to solder these things, I'll be using this flux, lead-free tinning flux. It basically is a chemical that coats the metal and protects it from oxidization when you heat it up. It also kind of cleans it and etches it somewhat. Makes the lead easier to stick to the metal. So this is a lead-free electrical solder. I'm going to be using that. I'm going to cut off little bits of it and put it around the edge, and when the metal heats up enough, it'll suck into the cracks as it melts. I've got my propane torch here, and I've got propane. I have a little butane hand torch, which would be okay for small jobs, but it's not going to be able to put enough heat into these metal pieces to melt the lead.
And now we're going to prepare the metal for soldering. First, I take a Q-tip dipped in acetone. I wipe everything down to remove all oils, dirt, and other contaminants that would prevent successful soldering. You want the Q-tip to look dingy gray or brown once you're done. You also want to use a fresh Q-tip for every piece of metal you solder. this paste flux is a lot more doughy than the solder flux that I'm used to using. So it's not as easy to control, and what you're seeing here is me applying too much. All you really need is a thin film all over every surface that you need solder to stick to. So you coat everything. You coat the inside of the hole, you coat the outside of the hole, you coat the mating part. You don't rely on any of the surfaces to transfer solder to each other once they're heated up. That's an easy way to get things oxidized. Now I'm mating the parts together. I put a solder ring around the bushing, and I'm using another piece of angle to keep it straight. The bushing doesn't need to sit crooked on the hole. I'm using a propane flame to heat up the steel. You want to heat the steel and the brass so the solder joins to them. You don't heat up the solder directly with the flame, otherwise it won't stick to the metal. If it was a smaller workpiece, a butane torch would be sufficient, but I need to make sure that it works because I don't want to have to undo this and do it again. At this point, it might look like I'm directing the flame at the solder, but I'm actually pointing it under the metal bracket. You want the heat to come from below so that gravity causes the liquid solder to run down into the joint. Capillary action will cause solder to flow into two very closely fitting pieces of metal when there's a small gap. That's why I cut the bushings to a smaller diameter than the hole itself, so they fit in kind of loose. Pick up the piece with pliers and inspect the joint. You might see solder on the other side. Here I am doing it again. Again, I preform the solder rings, and I just stick them over the work. When the solder melts, I know I'm done. We clean the larger pieces and apply solder in the same way we did the smaller ones. When you solder a joint, you let the joint cool for a few seconds before you handle it or move it. If you don't, that can cause the solder not to solidify correctly, and you may get a very inferior joint. This is called a cold solder joint in electronics, and it's the bane of a lot of beginners, not being able to solder correctly. Some people might say I should silver solder this instead of using a soft electrical solder. Silver soldering is very expensive and uses a very high temperature, meaning I would have to sit here a lot longer with the propane torch to get the metal almost red hot. Being that these solder joints will not experience extreme mechanical forces like they would in something like a boiler, I'm not going to use silver solder. I'm going to save it for where I really need it. I cut the solder into these little preformed rings that are almost the exact same size as the bushings. When I put them down onto the metal and then apply heat, it melts as soon as the metal's hot enough, meaning I'm not blasting more heat than necessary, overheating the work, or burning the flux. I don't know what happens if you burn the flux because I've never done it, but I don't want to find out. Like you see here, it melts into a liquid silver type material and immediately goes concave as it sucks down into the joint between the brass and the steel parts. You want to make sure to move the flame around so that the metal on all sides is hot enough to melt the joint. Otherwise, some of the solder won't melt and you'll result in an incomplete joint. After I finished soldering everything, I hit all the steel parts with a wire brush. This took off all the scale and extra flux and cleaned everything up. I wanted everything to be nice and clean before I applied some clear acrylic to seal the steel and make sure it wasn't going to rust.
The bushings are all soldered in. I've cleaned up everything with a wire brush and sprayed some clear acrylic so that the steel doesn't rust. Next, I'll be locating the steel parts on the wooden base and installing the steel rods. Pretty soon this will start to look like an actual machine. See you next time.